Hello everyone, welcome to lecture 2 of ECE 113 Communication Electronics. In this lecture, we will be talking about the noise in electronic systems and how do we model the effect of noise. Right, so we're still not departing from the system view of our communication systems. This lecture serves to enhance the system view. Right? Particularly, we want to know how noise behaves in your communication system, or actually in any system in general. Okay? So, noise, as you know, is an inherent property of any, or an inherent signal that is always present in any electronic system. What are its sources? So, let's recall that your electronic systems use electron flow for it to work. So any component of your circuits uses electrons for it to work. Electrons are negatively charged, they tend to repel each other. And if you collect a lot of electrons, and it's a lot when we're talking about our wires, our capacitors, resistors, inductors, amplifiers, etc., etc., your electrons will randomly move around, even if there is no external voltage. The average current is zero, since there is no net flow, but there is still a flow of electrons. So the electronic noise actually comes from different sources. Your thermal noise, the non-zero temperature, which lets the electrons flow, causes the vibration of charges, etc., etc. Shot noise found in our transistors, your diodes, any nonlinear device, and vacuum tube device. This is due to the weird behavior in our semiconductor devices. Flicker noise, noise that occurs in most electronic devices and some others like quantum noise, cosmological noise, plasma noise, even interference from other sources, etc., etc. So we're only going to look at the thermal noise. So the thermal noise, consider a resistor that is not powered by any voltage source. If you try to measure the voltage across this resistor, some resistor with temperature T, you'll actually get some V sub n, okay? So V sub n of t, a random process. So this is a random process, and it's modeled as a wide-sense stationary random process. That means it has a constant constant mean. Therefore, at any point in time, if you measure the mean of the random process, you still get the same mean. And the mean is actually zero. Since there is no net current flow in your resistor, there should be no net voltage. So the average current is zero, and the average voltage is zero. The autocorrelation defines the power of the noise. So how do you compute the noise power? Well, power is directly related to voltage squared, so let's compute that first. Let's get the average voltage of voltage squared of our noise signal, and that is equal to this, and that is actually equal to this equation right here, and this is from Planck's black body radiation law, right? So the RMS voltage of the noise is equal to, just get the square root of that right here. Okay? So that is your RMS noise voltage, the bandwidth of the system, your resistance value, the frequency, Planck's constant, Boltzmann's constant, the temperature, and Euler's. Okay. So this is Planck's constant and this is Boltzmann constant. So if we're going to consider RF frequencies, so a loose definition of an RF frequency, sorry, that's redundant. The loose definition of radio frequency is until 300 gigahertz. Right? Anything beyond that is what it's already your from your infrared to your visible light. So anything less than 300 gigahertz, this is your radio frequency. Okay? So if we evaluate the noise, so the maximum frequency is loosely defined as at 300 gigahertz. So let's look at the denominator of our thermal noise. Okay? So H times F, if F is 300 gigahertz, that is equal to this equation right here, this value right here. At a temperature of room temperature is approximately 290 Kelvin. And that is K times T, your Boltzmann times your temperature, you get this value. So if we get HF over KT, we actually have a value that is around 10 to the minus 1. Okay? And that would mean that this HF over KT can be seen as much less than 1. Therefore, if it's much less than 1, okay, using Taylor series approximation, this HF over KT will just be will just come out of your Euler Euler exponent. Okay? So using that approximation, this denominator will become HF over KT, and it turns out that the RMS noise voltage is just a constant in terms of frequency. Okay? So it's constant of frequency. What does that mean? That means it is white. It is white noise. Okay? Which is the assumed noise in our communication systems. Alright? So our approximation or our assumption from our EEE 107 course that says noise is white, right? It's white and Gaussian distributed. At least the white noise part is actually a valid approximation or a valid assumption rather. Okay, so this actually proves that for RF at least we have a white noise that comes from the thermal noise. Okay? So just some note that if we're talking about the standard room temperature in Kelvin, so that's T naught, and we assume that's 290 Kelvin. Okay? Alright, so it turns out that we can model our resistor at a temperature T of K. We can model that as a voltage source whose output is your noise, and then we have a noiseless resistor R, and we have your V of T right here. This is actually just a Thevenin equivalent of this resistor. What do you know? It has a Thevenin equivalent, right? So anyway, so this is an equivalent circuit. And if we're going to put another resistor here, what would happen to the noise power? Or how would the noise behave? Okay. In a lot of cases, your RF circuits are matched to each other. So what do we mean by that? The output resistance from the previous block is equal to the input resistance on the next block. So this is the maximum power transfer case. If the circuits match, how much noise power comes in this receiving resistor? So we can solve that. We have V of T equal to, basically, we're just going to do a voltage division. Since the resistors are equal, the voltage is 1/2 of your random signal Vn of T. If we're operating at room temperature, then the power at the receiver resistor is V squared over R, V squared being the voltage here, specifically the RMS voltage. Okay? The RMS voltage of V squared here is 1/2 of the RMS voltage of Vn. Okay? So if you take the square of that, then it turns out that the power received by the resistor is 1/4 of Vn, which is Vn squared, which is equal to this value right here. So the 4 will cancel out. The resistor value will cancel out. The power turns out to be equal to KT naught B right here. So this is the noise power received when we have a matched resistance case. Okay? From there, we can now define what we call the equivalent noise temperature of our system. So consider a system. So system block, at least. We have a noisy block right here. The equivalent noise temperature, assuming that the input resistor right here is operates at absolute zero, we observe some noise at the resistor right here, and assuming we have a matched circuit from here to here, then the power of the noise, the power of the noise is equal to K times the temperature, some temperature, times the bandwidth of the system. So this temperature right here is called the equivalent noise temperature. And it's equal to the noise output of your noisy block, assuming that there is no noise in its input. Okay, so that's the noise right here divided by K times the bandwidth, where K is Boltzmann's constant. Okay, so basically this is just a wordy explanation of what I showed earlier. Okay, and the main assumption here is that our systems are matched. Okay, so the equivalent noise temperature is equal to the noise output of your noisy amplifier, given that there is no noise here. All right, and we have this. So your noisy amplifier actually adds noise into the system. But we can think of it as something like this. So your noiseless amplifier is connected to a noisy resistor. All right? Okay? So your noisy amplifier is connected to your noiseless amplifier is connected to your noisy resistor, and the noise that is fed here will be multiplied by a gain of G, and then it will be fed to the other resistor. That's why the equivalent noise temperature of a block with some gain is equal to this divided by the gain times your Boltzmann's constant times the bandwidth. Okay? So this is your this is your equivalent noise temperature. And each block has some form of equivalent noise temperature. Right? Even a resistor has its own equivalent noise temperature. Okay? So let's define what we call the noise figure. This is a metric that we use to characterize the added noise from a system block. Its basic definition is that you just get the ratio of the input SNR and the output SNR. This is your noise factor. Okay? Noise figure would be in dB, and that's just basically the dB version of this. So generally, we'll just this is the definition of noise factor for it's linear. In dB, it's noise figure. Let's collectively refer to them as noise figure only. Okay? So some notes, your mixers use active devices, and generally they have a large noise figure. Your LNA has a high gain and has a low noise figure. So what do we do with that information? You'll see. So for the amplifier, let Si of t be the input signal, and I of t would be the noise at the input. So of t would be the signal at the output, and N naught of t would be the noise at the output. Your amplifier has an equivalent noise temperature T sub E. Okay? So now let's let some variables be your SI, your input signal power, NI noise power input, SO is output signal power, and NO is output noise power. Therefore, our input SNR is equal to SI over KT naught B. So this is the noise power, assuming that our system here is matched with the resistor here. Right? So it's important to know that. Okay? So assume that it is matched. So our input SNR is equal to your input signal power divided by your noise power, which is KT naught B. Okay? The amplifier has a gain G with equivalent noise temperature TE. Therefore, the noise contributed by the amplifier, so it's contributed by the amplifier, is equal to the gain of your amplifier times KTEB. Alright? So to solve for the noise figure, we need to know the output noise. And the output noise is equal to the gain times the input noise. So the noise from this resistor will be amplified by the amplifier. Okay? And the amplifier in itself adds some form of noise. So this N sub I here is equal to K times T naught times B. So that is the temperature, initial temperature of the resistor. And then we have this expression for the output noise. Finally, the output SNR is just your signal power output divided by your noise output. The signal output is equal to the gain of the amplifier times S sub I, which is the signal input power. Therefore, G will just cancel each other and we'll be left with this value right here. Okay? Alright, so now to solve for the noise figure of the system, we'll just divide this SNR in with the SNR out. Right, so G will cancel each other, KB will cancel with each other, SI will cancel with each other. We'll be left with T naught plus TE over T naught. And this is the noise figure of your amplifier. So the amplifier is F is equal to 1 plus T, noise figure is 1 plus TE over T naught. Follows that your equivalent noise temperature is equal to F minus 1 times T naught. So note that the system is matched and the noise figure is only dependent on your equivalent temperature and the ambient temperature of your circuit. And this actually provides a characterization of how much noise is added by your device. Okay? The higher your equivalent noise temperature, the more noise you inject in your circuit or in your system. So this also applies to passive networks. So for example, your low noise amplifier, let's say it has a bandwidth of 20 megahertz and equivalent noise temperature of 75 Kelvin. If the input is kept at 290 Kelvin, what is the noise figure of the amplifier? Assuming your input power is 10 nanowatts, what is the SNR at the output? So we have the formula already. Your F is equal to 1 plus T over T naught. And that is equal to, in linear form, it's equal to this. And in dB form, it's equal to this. Solving for the input SNR, well, we have S sub I, we don't know your, the input power is 10 nanowatts, and KT naught B can be solved using this for bandwidth. T naught is 290 Kelvin, and K is your Boltzmann constant. We have this value in dB. We have 50.96. So basically, to solve for SNR out, you just need to get the difference of SNR in minus F. You get SNR out. Okay? Now, the real good thing about knowing the noise figure is that if we now cascade our system blocks, how does the noise figure behave? Or how do we solve for the noise figure? So each block has its own equivalent noise temperature. Okay? And as always, if we're gonna look at it as one big block, then we're just gonna solve for the input SNR divided by the output SNR. So solve for the noise at the output first. At the input, we have N naught equals KT naught B, and 1 is equal to, so it has a noise that is fed to this first block. It will be amplified, and some other noise will be added. So that's what you have here. Okay? And it's the same with our second block. Some noise N1 will be added, and will be fed, and some noise will be added. The noise that is fed to the second system block is amplified by that block. So we have this expression for N2. Substituting N1 here and N0 here, we get this expression for N2. Okay? So now the total noise figure is SNR in divided by SNR out. So if you look at this expression right here, K will be cancelled, B is cancelled, G1 and G2 are cancelled here, S0 is cancelled, and it follows that our noise figure is equal to this divided by this T0 right there. So you have this expression right here, okay? And then we have this expression for your noise figure for the cascaded block. Okay? And note that this 1 plus T over T0, that is your first noise figure. That's the noise figure of this first block. So that's F1. Your F2 cannot be seen here, but we know that this is related to F2 right here. So F2 is the noise figure of this block. So finally, we have the noise figure, the total noise figure of the system as a function of the noise figures of the individual blocks. So we have this one for a cascade of two systems. So notice that the gain of the first block affects the contribution of the second block's noise figure. Right? If we're going to use a low noise amplifier here, a property of the low noise amplifier is that high gain, low noise factor. So if we use a low noise amplifier, G is very big, then the noise factor of your second block will be attenuated by this low noise amplifier, keeping your noise factor, your system noise factor, to a reasonable value. So that's actually a use of your low noise amplifier. Right? If you switched it around, then the performance of your low noise of your system rather would be bad. All right. Generally, now, if you're going to look at a whole cascaded system, the total noise figure of the system is equal to this. Okay? So the gain of each block will cascade and affect the noise figure contribution of each succeeding system. Okay? And just note, this is where a lot of people make mistakes. The noise factor here is in linear form. Okay? So convert your dB first to linear before you solve for the noise factor. Alright. So for example, we have a generic receiver. Compute for the overall noise factor of the system. So this BPF is passive. Okay? So it's passive, then let's say it's noiseless for now. So I did not discuss any passive effect of passive system. So let's say it's noiseless for now. Okay. So what happens is we can think of this as one system. The mixer absorbs the effect of the bandpass filter. Alright? So the bandpass filter reduces signal power before the mixer. And we can let the bandpass filter absorb the mixer. Since it's noiseless, it doesn't have any noise factor, or the noise factor is 0, then we can also let this LNA absorb the BPF. Okay? So we have this noise figure uh, of your low noise amplifier plus 1 over the total gain of your amplifier plus your filter. We have this we have this expression, which is 9 dB times the noise figure of your mixer minus 1. Okay, so that 2 dB noise figure of your LNA will be converted to linear first. Same is true with your mixer. And your 9 dB gain is also converted to linear. So we have this final value of your noise figure for your generic receiver. Okay. So in reality though, your BPF also adds noise. Okay. The noise figure of your any passive system, for example, your BPF, is actually equal to how much loss it it creates, okay, or how much attenuation it has. Okay, so this BPF has its own noise factor. Okay. So for this example, we are considering BPF to be noiseless. All right. So next, final topic or final property of noise is that for every system, there is what we call an equivalent noise bandwidth. Okay? So basically, your noise passes through a frequency response, h of f. Okay? The noise equivalent noise bandwidth would be the bandwidth b sub n such that it can be modeled as an ideal low-pass filter with the same area. Right? This ideal low-pass filter will have the same area as the area under the curve of h of f. Okay? So don't mind all this explanation. Okay? We just want to find b sub n such that if it is an ideal low-pass filter, okay, the area of that low-pass filter is equal to the area of the total frequency response. Okay, and we have this actually. All right. So because of that, the total noise is equal to n naught times b sub n. So that b sub n has a height of h of 0. Therefore, h of 0 squared times the bandwidth, it should have the same value as the area under the curve of your magnitude response squared. Okay? So, oops. Let me erase that. No, it doesn't want to be erased. There you go. Okay. So now this B sub n is the equivalent noise bandwidth of the system. And this actually limits the noise power observed at the output. In reality, actually, if you're going to consider the whole frequency band, the noise power is unlimited. Okay. But if we have a filter or something with a frequency selective device, then we can limit the bandwidth of the noise. Okay? So our noise power will be limited by this noise bandwidth. That will be equal to kT times B sub n. So if you have a system and the operational bandwidth is not given, you need to solve for the noise bandwidth of the system first. Okay, anyway, for example, what is the equivalent noise of your low-pass filter? So the frequency response of your low-pass filter is h of f. Then we have h of 0 at f0 is 1. So using this equation, here, and we integrate this h of f, the magnitude of h of f squared, we have this. You can already solve this if you let theta be equal to this 2 pi frc, tangent theta rather. So this is trigonometric substitution. And you'll get the noise bandwidth of a low-pass RC filter to be equal to 1 over 2 times RC. Excuse me. Okay? So that's the end of this lecture. So if you have any questions, do not hesitate again to leave a comment in the comment section below. Thank you for listening. I'll see you next meeting. Bye.